Hi, everyone. Thank you for this June edition of the AICE Working Group online meeting. Today, we are welcoming our friends from the CEA List Research Lab, and they are going to present us at the N2D2 project. But before that, a small introduction to the working group for those who don't know it already. Some news on quick news on the working group. Then we will leave the floor to CEA List friends, and then the next steps of the working group and the question and answer, of course, quick question and answer session. So you can share with our participants. Today, that's the goal of this kind of sessions. So quick introduction. You know, I won't come back with the move to Europe. This is history now from the Eclipse Foundation. But with this move, we're now focusing on a few strategic projects tightly linked to the EU sovereignty. That's, let's say, cloud, edge, and including the cloud to edge continuum. And we also artificial intelligence is also gaining good momentum right now. And at the crossroad of all these technologies, we are building the AICE working group. So the AICE stands for Artificial Intelligence, Cloud and Edge. As you would have guessed, that's a new working group in under creation at Eclipse. And our intention is to build a great ecosystem to collaborate on AI in the open. And we have the ambition to run AI test beds on tools and different cloud and edge infrastructure. That's why we are combining this, all these technologies in one, all these topics in one working group. So what you see on the screen is the kind of requirements we are aiming to address in this collaboration. We want the AI to be trustable. We want it to be explainable, and we think that's open source is necessary to do it. And when you do open source, it enables interoperability. And when you talk about edge, embedded and frugality are necessary also. They are almost inevitable when you talk about edge. This is why we want to do it in the open, in an open source ecosystem. So that's the mission of the AICE working group, you know, to promote the advancement, the development, and the experimentation of open source software, open source technologies in mainly in an open lab. And so we will set up an open lab. We will ensure privacy, security, ethics, and the frugality requirements are met, and they are integrated, and they are by design into our works. Sorry. Some news now on the working group. So we are still in the incubation phase, the proposal phase, and still looking for gaining more momentum, more members to launch officially the working group after the summer session. For those who are not already on the mailing list, I've put back the slides to invite you to join the mailing list. This is where we can discuss and where we will send the next invitation for the next session of the working groups. So you just need to create an eclipse.org account. You can do it in 3 clicks and with your own email, and then you will be able to subscribe to the AICE working group mailing list. And now that just to give you an idea of our early supporters, that's people committed to do AI on cloud and edge in the open. So the Aura Healthcare, you've met them previously in May. They presented their demonstrator, what we've done with them in 2021. University, I'm sorry for the pronunciation of Skövde, maybe that's an university in Sweden. Synesthesia from Italy, Fraunhofer Focus, Laboratoire Focus from Fraunhofer, from Germany, Nusware from Belgium, SDIS, Sustainable Digital Infrastructure Alliance, who provided the computing power for the Aura demonstrator we did the last year. They're in Germany also, and the Bremen Institute also from Germany, AT Bremen. I won't go pronounce the exact way. I'm not a German guy, so sorry. And many thanks to them for committing to do AI in the open, with the Eclipse. So we want to grow the ecosystem, and we need you to help us grow this ecosystem. We need your project, your use cases, depending on what you can bring to this working group. Platform project, application, test beds, demonstrator, wishes project. If you want to disseminate them and to see what other people can do with them. We need computing power also. We need more partners, more projects, more ambassadors. So this is the first step of the working group. So your requirements will help frame the working group as you want it to be. This is your working group. I don't know, Gael, if you not want to add something before having a word on the.
That's fine.
Okay. Okay.
I think that it's a first approach and getting new projects, and there's really a point about reaching a critical mass in terms of the number of projects. We have already projects like deep learning for J, which was listed in an article recently as one of the 10 most important projects in open source about AI, and we want more of those projects.
A few words on the AICE website. So you've noticed since the previous meeting, so now the content is online. We have more content available. So the objectives of the working group are more clearly defined on the website. We have a testimonial. We have everything you need to know to join us, to participate, link to the mailing to the mailing list, news and event section, a resource section where you can find an updated version of the Aura demonstrated paper, thanks to Boris. And all the links to the video and slides from our previous events are now available on the AICE website. We are currently working with the marketing team at Eclipse to have a better, modern eye-candy design, and we hope to have it by in Q3, so in the coming months. So I hope to the next meeting, I hope to be able to present you the new design of our AICE website to be more sexy. So now the heart of our presentation today, that's the N2D2 project from the CEA List. And I will give you the floor. Just time to switch the presentation. Do you see the presentation?
Yeah, we see it.
Okay, just tell me when you want to move to the next slide. I'll give you the floor. Thank you, Ina and Sandrine.
Thank you. So today we will present you our project we are developing in CEA List. So the CEA List is one institution of the CEA where we are focusing on embedded systems in particular. So me and Sandrine, we are the part of the, we work in Liège. So it's a laboratory for, yes.
Sorry to interrupt, but we have a problem with the sound. Your sound is some kind of saturating or something like that.
Oh.
I don't know if you just lower the volume or something like that.
Okay. Is that better? Is it better?
Then that will help. I don't know.
Is it better now?
No.
No, it's okay for me.
Okay, sorry. So that's go ahead.
Is it okay for you?
Yeah, it is for me as well. It's okay.
It's okay.
Okay, that's on my side. Sorry about that. So I let you.
No problem. But don't hesitate to interrupt. Actually, if you have Any questions about the content or about the sound, or if something is not clear? Okay. So I go back to my presentation. So we are the part of the laboratory which is focusing on developing the embedded systems, and our team is working on developing a framework for artificial intelligence to be able to deploy the deep neural networks on different embedded systems, which we will see today. So we can go to the next slide. So our context and motivations are listed here. So as you know, and this is not a surprise, that for the moment behind every single major deep learning framework and developments and the breakthrough, for the moment those are US companies which belong to GAFAM Group, and relying totally on them means that we would buy their solutions and chips tomorrow, because we cannot integrate their codes on different systems. So in CEA List, we propose and we develop our own independent framework, which will be able to compete, and it's called N2D2. So our idea is to build their own tool chain from the algorithms to embed it on the hardware. So we integrate innovative methods as quantization, compression, and in the future, hopefully pruning, to be able to tailor the algorithms to the hardware. So the targeted high-level hardware generation is needed to reduce the cost and also development time, and also remain competitive on the sovereign technology node. So we want to master high-performance, large-scale trainings and implement them on the GPUs in order to build the best performing systems. So also we want to integrate the innovative methods for reliability, robustness, and dependability and explainability. So also we want to integrate the innovative method for lifelong continual learning. So for the first part of the presentation, I will present you what exists in N2D2 now, and after we will see the future of this project. So we can move to the next slide. So here we can see how it looks now. So we have a unique platform in order to design and explore deep neural networks applications. And in this part of the picture, you can see that we have the full tool chain going from the database for learning and testing of the neural networks. After we provide the modeling of the neural networks, either by our own descriptions, as we will see, or we can also take the ONNX type model, which is coming from other frameworks like PyTorch or TensorFlow. And after we provide the learning of the neural networks with the optimization. So you can click on the next part. So also we developed the quantization-aware training, on which I will stop a bit later into details. And this is the part of the optimization system during the training. And if we move further, we can see that in the framework, there is also available the post-training quantization. It happens when we already trained our neural network in the full precision, and after we want to quantize it to lower precisions from 2 to 8-bit integers. So if we move a bit further, the last step in the toolchain is to be able to generate the standalone independent code for different targets. And the last part is this code to be executed on those targets. So here we are talking about the generation of the code as C, C++ assembly, and also generating the code for high-level synthesis description or customer tell. So our targets are the classical targets as STM Trendo, NVIDIA, Calray, or could be also custom accelerators which are developed in CEA List. So we can move to the next slide. And here actually I also put the links. So our idea of the framework is that we want to be as open as possible. So we have different modules provided in the open source, and the link was on the previous slide. So we have the GitHub, which is open to the public, and here you can see what is available to the public. So those are in green boxes. So just to situate you on this slide is on the left, we can describe and model our models. So either by the native API, which we call ini file, we can see it a bit further, or now we also integrated the Python API in order to be able to be more user-friendly and also to be compatible with other frameworks. Or we can also take the ONNX format, as I mentioned before, and also we provide the integration of the Keras and PyTorch, as we will see in the future. So there could be also partner interfaces, but those would be under their license. So after you can see the core modules of the framework, which are described and written in C++ code. Those are called core modules. So in order to be able to take care of the database, the image transformations, and after we describe the layers of the neural networks as called cell here on this slide, which can also have different parameters and different objects like activation, the solver in order to override the parameters, and the quantizer, which is partially open source now, depending on the methods. And also we have fillers. So also there are targets and different exports, which are export generations, which are written in C++. So for the export modules, you can see that many of those are under license, and we have also the C++ export and TensorRT, which are open source. So and on the last part, you can see that we can specialize ourselves for different needs of our industrial partners in order to customize the export. So we can move to the next slide. So here you can see the ONNX compatibility, which was mentioned before. And so N2D2 is one of the frameworks which are compatible with the ONNX, which is shown on the left. And after we can deploy, optimize and deploy this ONNX model through N2D2 in order to be able to be executed in inference in different targets. So we can move on to the next slide. So now I will stop a bit on the quantization discussion because those modules are actually the latest one we developed in our team, and those are the modules which interest a lot our partners. So the first one is quantization aware training, which is presented here. So in N2D2, we implemented two different methods, which are state-of-the-art methods and give us the best performance results. So the first one, which is a bit simpler, is called Lorentz step size quantization. So for both and the second one is scale adjusted training, and I added the links to the papers. So both provide us the weights and activation quantization support. Just to illustrate what I mean by the quantization is illustrated on those two graphs. So on the left one, you can see the distribution of the weights of one of the layers in the network. And we can see that here, for example, it could be nice, smooth Gaussian distribution. And when we quantize, which is actually what we call fake quantization, because here on the right you can see we don't fall into the true integers numbers like 1, 2, 3, 4, etc. We are still in the same range as the full precision weights, but what happens is just our distribution becomes discretized, and it has the number of bins which are equal the number, the range we wanted to quantize. So here, for example, you see 4 bits weight distribution. So this is how it looks in the network. And so how we do it, we start from the full precision model, and this is our starting point. And after we provide the full retraining with a certain number of epochs in order to adjust those distributions and find the best redistribution between the left and the right plot. So what is nice about the first method, learned step size quantization, is that for 8-bit quantization, it requires just one epoch training. For example, if our network is extremely huge one and heavy, and we just want to see how it would perform in 8-bit, it suffices only one epoch, and it gives us very nice results. So we think it's going to be our solution to the post-training quantization, which I will discuss just after. So the second method, it actually outperforms LSQ method, at least on the networks we tested, which are mobile net type networks. But the fine-tuning process is extremely long. It's at least 150 epochs for the mobile nets, but we know that mobile nets are very compact networks. So if your network has a much more parameter, the process would be prohibitively long in order to quantize it. So for the moment, it's our quantization reference, but I think we would have to find a compromise between those two methods and between the time of the quantization and the result we want to get. So we can move to the next slide. So just to tell you a bit about the training flow and why it could be very long. So the principle is to take into account the required precision during the training. So we take the full precision weight, for example, of the convolution layer, which is the usual structure we deal with is shown on the right. So you can see that we can have the topology as the convolution layer, followed by the normalization of the batch layer, and after we have the activation. So now we want to quantize this structure. So we take the full precision weights of the convolution layer, and we quantize them prior to the convolution operation. After we provide this operation, and we pass the output of this layer to the batch normalization layer. And at the end of this operation, the output of this batch normalization layer is quantized. So in this way, the network adjusts both quantized and the full precision data. So during the training, we keep track of all of those quantities for weights and activations if we quantize them both. And we do it through the classical backpropagation process. So at the end of the training, the network adjusts its parameters for the particular required precision. So we can move to the next slide. So just to show you some results, which are actually also available in our documentation on the website, which is, I added the link here. So you can see that for the mobile net, we applied the scale adjusted training, and we were able to reproduce the paper results. And here, if you see the first line, so the usual performance of MobileNet V version 1 is about 70 to 73% in the full precision. And for 8-bit weights and activation, we get actually the same result. And if you look at the precision for 4 bits, you can see that we lose about 1.5%, but we quantize for 4 bits of weights and activation. So in our team, we also developed another method in order to be able to quantize our activations lower than 4 bits. So this is what you can see in the last couple of lines here. So we provide those results. So the patent is being deposited right now. And so this is the reason actually we don't have everything in open source, because we want to deposit this patent before. So we can move to the next slide. So here I want to come back for the post-training quantization. So if you remember the schema in the beginning, so these modules comes after we train our network. So in this case, we have the classical training in the full precision, and after we want to quantize our network. So for this, the advantage of this method is we don't need to retrain our network. We just apply it afterwards. So there are 3 different steps which have to be applied for this. So we have to renormalize the weights and activations first. So, and the usual renormalization ranges are -1 and 1 for weights. And it can be done either per layer or per layer and per output channel normalization, which gives us more fine-grained results. So for activation, it's the ranges are between -1 and 1 for signed outputs and between 0 and 1 for unsigned ones. So afterwards, we want to find the optimal quantization threshold value, and we will see how we do it in the next slide. So this is also an iterative process, and it means we need to take into account the previous layer normalization factors. So after we come to the quantization part, we actually need to convert the ranges from -1 and 1 in order to fit in the number of bits required. And here we just have to recalibrate ourselves in the right ranges. So we can move to the next one. So here, in order to find optimal quantization threshold values for the activation, we need also to propagate our input data in order to have the outputs of each layer. And this is what you can see on this slide. It's the output value of one of the layers of the network. And afterwards, we need to find a threshold that minimizes the distance between the original distribution in full precision and the quantized distributions by using one of the 2 methods, either the mean squared error or a Kell divergence algorithm. So the threshold value would be our activation scaling factor, which we would have to take into account during the quantization. So we can move to the next slide. So the performance which could be seen here are done with the MobileNet V2 from the classical ONNX model done in PyTorch. And here you can see with different steps how we can lose the precision. So what can we see here is that in 8 bits, we lose at the end something like 4%. And as we've seen just before, applying quantized training quantization, so we don't lose any precision at 8 bits over a few, depending on the model. So this is also the reason we are suggesting to move forward with the QAT type of quantization in our framework. But for the moment, we have both available. So we can move to the next slide. So after we calibrated our network and quantized it to the desired precision, we can proceed with exporting it in different targets. So here it's a slide just to illustrate you the different targets available, like GPU, CPU, the microcontroller like type STM32, and we have also the customized and the proper AP like for the FPGA called DNN, and we will see a couple of illustrations what we can do with it here. And also we have the export, which can export not only the classical tensor-like networks, but also the spike neural networks. So we can move to the next slide, please. So just showing you how the idea of the export with with the export, and here the example we took is for the FPGA with our proper IP called DNN. So we start with a description in 2D2 native format, which is in format, and after we can recalibrate our network as we've seen here. So calibration here in the middle corresponds to the post-training quantization, which I mentioned just before. And after we can generate the code, we can generate the RTL in order to provide the description to our target. So, and after we also have the emulator for the neuron. So we can move to the next slide. So here in the team, we also can do different optimizations in order to provide the most performance code which can be executed on FPGA. So I will not go into all those details here, but the main point is to tell you that we support the classical layers in the convolutional neural networks, like convolutions and also fully connected layers. And so this is the work which is presented here is quite of the legacy work, we can say. And now we are working in order to integrate the QRT support, but also not only for FPGA, but also for the multi-targets like ASIC plus FPGA, in order to do different tasks like the image classification, but also segmentation and object detection. We work with the type of the object detection SSD. And so this is work in progress, and for the moment we do not share it here. So we can move to the next slide. So here is the principle, the working principle for the DNN, the optimizations which can be done. So those are the first part is the reorganization of the data in order to be able to provide it into the good format to be executed on the FPGA module. And the second part is also the optimization in order to be able to do the computations into the parallel. So we can go to the next one. So here is just the FPGA demonstrator, which has been developed, which was developed in our team. So the idea is to see in the real time the pixel-wise segmentation. So you have the map as shown on the left, and after we can see that we are able to do the pixel-wise segmentation in the real time using this DNN FPGA demonstrator. So you can see on the right that it finds different objects and assign the pixels to those objects as shown on the right. So we can move to the next slide, please. So one of the modules we developed very recently is to be able to be compatible with PyTorch and Keras, and this is extremely important nowadays, as you've seen from the first slide that we are dominated by those frameworks. So we want to be compatible with them and provide the kind of interface to our users so they can be able to write their models in the Keras style, for example, as shown here on this slide. And after in the backend, we would have N2D2 providing the training, quantization, and also different optimized exports. So we can move to the next slide. So here, those are just highlights in the future works we are planning. But for the future works, I have a couple of more slides to present you the new project which just has started. So just to summarize here, our very recent developments, quantization aware training, and also we developed the Python IP in order to be more user-friendly and to facilitate the usage of N2D2 framework. So we also want to optimize lower than 8-bit C++ inference export, and this is work in progress. And if we move to the next slide, I will present you our new project, which is the continuation of N2D2 work. So here I just take the same idea as I've shown you in the very beginning, and I want to tell you why we want to develop N2D2 even more. And for this, we've got the grant from France in order to be able to do it. So here, those are some of the main goals of the project. So we want to take N2D2 into the next level and to develop it even more. So in order to provide a software platform that specifically meets the needs of for the embedded targets. Also, we insist on the fact that the code has to be open source. Also, it has to be durable and it has to be available for the European market. So we want to facilitate the choice of hardware targets and accelerate the deployment of those networks on embedded targets. Also, we want to take the European suppliers of components and hardware IP on the same level as American players. And with the second part of the project, which I will discuss in a minute, we want to give the startups and the industrial users the tools to deploy their artificial intelligence algorithms on the large scale of various embedded targets. So in very constrained environments. And also we want to give our consortium members the possibility to contribute to the development of this platform itself, and also to orient the choice of functionalities according to their own needs. So those are the main goals. And if we move to the next slide, we can see here a bit more the actors which responded to our call. So they are coming from different areas like mobility area, the defense, aerospace, manufacturing, energy and health. And after in the middle we have the N2D2 framework, which I just presented you. And at the end we would have different suppliers of the IPs, like the components of the shelf or integrated circuits providers. So both for high performance systems and also for the lower power systems. We can move to the next slide. So here I just show you our main guidelines for this project and also the motivations. So we want to have our own independent platform for innovation, and in order to be able to develop and integrate innovative algorithms for the embedded systems. So also we want to be very performant and interoperable with different frameworks, and also we aim to provide high-level material design and synthesis in order to have lower environmental impact, which has become more and more important. And we want to integrate all those constraints which are becoming more and more problematic for the AI domain, like reliability, safety, and the trust constraints. We can move to the next slide. So here I just show you the plan. So in a very high-level way, in sense of what we want to do. So we have two different parts in the delivering project. We have the part for the core development, as shown on the left, where we want to develop our platform even more by providing more various algorithms in order to optimize our networks. Also, we want to have high-level hardware design and benchmarking, And we have the part which will take care of the algorithms to develop the trust for embedded devices. And as I've shown you before, we also want to be, from the technical point of view, very performant, and to integrate all those tools as other framework like continuous integrations, and to be able to be compatible with them. So also we want to integrate the hardware components, which is takes us to the second part. So we have the part with the industrial partners, and those are the partners which are responded to our call for the moment, and they're listed here on the right. So I think this brings me to my conclusion. So I presented you our framework as it is now, and here you can see the first look of our plans, how we want to develop it. And so this project just has started, and we are eager to see where it brings us. Thank you.
Thank you, Ina. Very interesting, very technical and interesting presentation. Maybe we have questions from the audience.
Yeah, I have 2 questions.
Go on, JB.
Yeah, the first question is, do you have some kind of relationship with all the open source projects that do part, not exactly the same as you are doing, but part of your, I'm thinking about the hardware abstraction layer. There are some open source projects like Apache, Wayang, and others that do something similar. Do you have some interaction with them, or is it something that you build from scratch completely? So that's the first question. And the second question is, what, in terms of open source, what you plan to expand the community and to recruit new contributors on the project? Do you have already some ideas in mind? Obviously, we can help. That's the purpose of the working group and the Eclipse Foundation. But do you already have some ideas in mind to recruit additional members and contributors? That's my 2 questions.
Okay, I will start with the first one. So we build our hardware IPs from scratch. So we didn't, we were not, at least for the moment, in the contact with the teams you mentioned. So at least not as I know of. So this is the first answer. And for the second one, I don't know if Sandrine you want to answer.
Just a question. What company are you representing?
So I'm representing 2 things. I'm representing the Apache Software Foundation because I'm an Apache member, and working closely with Florent Gaël and others at Eclipse. And I also open source ecosystem development at Huawei. And I'm French, by the way.
Okay.
Just to be clear.
Okay. Okay. So so we put N2D2 in open source because we are conscious that it is the only way to be well used by the widest industries and also research members. But politically, so we start with promotion of the tool at a national part, and we with the Deep Green project, but we also had a European project in order to start the promotion at a European level with the new members. So we have several partners on hardware part with French actors such as AICE, NanoExplore, Calray, Dolphin Design, and we extend that partnership with other companies such as NXP, Grey Matter Lab for the European part. And we have the idea to extend those promotion activities. So this is also why we are discussing with Eclipse. But today it is it is not fixed how we will do it.
Okay, okay, that makes sense. Okay, interesting. Thank you.
Any other question?
Yeah, I have a question. You said that everything was not open source. Florence Zara from Eclipse. You said everything was not open source at the beginning, sometimes because of there was a patent pending, but once the patent will be granted, will you open and put in open source your patented technology?
Yes.
Or?
Yes, yes, yes. As soon as it's deposited and safe, let's say, as we ensure that it will be our property, we put it in open source. Yes, this is a plan.
Okay.
Which is perfectly fine from my perspective. I mean, we have the only limit on using patent with software under Apache software license or the Eclipse license, for example, is that, of course, you have to provide a royalty-free license to your patent for the usage of this exact code, but you can still sell licenses to your patent in other contexts.
Currently, I've seen that the open source license used is the Cecil C license for the whole code, or just for the some part. Do you have a mix of license for your own code, or everything is under Cecil C license?
I think for the moment, everything is under Cecil. Boris.
Thank you. So I'm trying to understand what is the scope exactly of the various parts, because as I see it, there are two different offerings, but I'm not sure. The part with the libraries and the hyperparameters, optimization, and so on. And there is this part about the execution. So is it one single big project, or are they two different projects?
Yeah.
Is the scope exactly of that, please?
Yeah, we can stay here. It's a good slide. So actually, it's a good question, but the answer is that our aim is the last part. So why we are optimizing those networks and what we are doing it. I mean, we developed the quantization, and we want to develop other different algorithms of optimization in order to be able be very performant and very fast on the various different targets. So whatever we are doing is always dedicated to the embedded part, because otherwise we couldn't be standing out enough than PyTorch or Keras or whatever other framework. So we are specialized in order to provide the efficient code on the target.
Okay, thank you. And regarding the mapping between the various frameworks that you integrated with, is it a 100% mapping? How say that I've developed a full toolchain and pipelines with say PyTorch or whatever, and how sure can I be that that can translate into your optimizations 100%? Do you have some kind of covering for that?
So for the moment, it's still work in progress, and what is developed in the Python API is mostly the left part. So all the code generation is still ongoing. As far as I know, in the C++ code. So this is still work in progress. But what you can be sure of, if you have your model developed, let's say in PyTorch, and after you want to apply our optimization of quantization, for example, you can still write your script as if you were doing the PyTorch. and saying you load your model, and after you call the method to quantize, you write model QAT, this name of the module quantize, and it will do it for you. So this is working, and we have the tests covering all of this. But for the code generation, of course, the goal is to be able to do all of this in Python, and for the code generation part, the work is still ongoing, and the more testing has to be done.
Okay. Okay, thank you.
Okay, I think we need to switch to the conclusion, Florent, because
yes, time is.
Lots of us should have meetings in 4 minutes. So.
Okay, to come back to the presentation, and now the next. Next step, what's coming next? So there is we will have a break for the monthly meeting during the summer season. So we will be back in September. I'm still working on a presentation, so I can't announce anything right now, but I hope to have a good presentation in September. If you want to present something, do not hesitate to come back to me or to Gaël. We can make room for you in the September maybe or October session. And speaking of October, we are planning to have a face-to-face meeting for those who will be able to attend EclipseCon 22 in Ludwigsburg, Germany, October 24th. Save the date. That's the community day of the next EclipseCon. So if you can make it there, we will happily welcome you for a community session. And that's it. If you have any question regarding the group, do not hesitate. If not, we can conclude our monthly session. And thanks a lot for attending, and thanks a lot, Ina, for presenting this really, really interesting N2D2 project.
Yes, thank you very much, Sandrine and Ina. I will call you because I have lots of follow-up ideas after this presentation. Thanks for the presentation.
Bye-bye. Have a nice day.
Thank you.
Thank you. Bye-bye.
Thank you. Bye.
Thank you. Bye.